Hello everyone, in this video I will be discussing some of the basic principles of acid-base titration, including the calculations involved and the process of summarizing the experiment. Okay, so let's just start with a definition of titration. Now, first of all, you need to remember that titration is a quantitative technique. So a quantitative technique is a technique that is used to determine the amount of something. And so it is a quantitative technique which accurately determines the concentration of a dissolved substance in a solution. So it's a technique used when you have a substance that is soluble in water and you want to work out the concentration of that substance in water. And this involves a chemical reaction between a solution of unknown concentration and a solution of known concentration. So you're always going to have at least two solutions in a titration experiment, and most of the time you only have two. One is the unknown, so you know what the solution is, but you don't know what its concentration is. That's the unknown part. And another solution, you know the identity as well as its concentration. Another name for a solution of known concentration is a standard solution, which I don't know whether you remember, but we actually have mentioned this in the past. So you need a standard solution so that you can determine the concentration of another solution. We only focus on direct acid-base titration this year, and then next year we'll look at direct redox titration as well. But just keep in mind that this is not the only type of titration possible. There is another method called back titration, but we no longer talk about it. All right, I'm going to just start with question one. This is an example of a titration experiment. There are a few terminologies and a few pieces of equipment that I want to remind you, and then we'll go through how we can analyze the data from this experiment to answer the question, which is determine the concentration. All right, so let's just start with this. A titration experiment is conducted to determine the concentration of a solution of hydrochloric acid. The most important thing when you read a titration question is you need to remember the purpose of the experiment. And this applies to any experiment, not just titration. When you do an experiment, you need to know what is it that you're trying to achieve ultimately. For every titration experiment, you're trying to find the amount of something, most of the time the form of concentration, but could be mass and other forms as well. So ultimately what I want is concentration of hydrochloric acid. This is the solution of unknown concentration here. And I am going to do that. I'm going to find the concentration of hydrochloric acid by titrating. So the verb titrate, I'll show you what titrate means in a second. But it's basically mean doing a titration experiment. So by titrating it with a standard solution, now if they say standard solution of sodium hydroxide, that implies that you know the concentration of sodium hydroxide, so known concentration. A standard solution is a solution of known concentration. So I know the concentration of sodium hydroxide, and I need to conduct an experiment to determine the concentration of hydrochloric acid. Okay, so the steps of the experiment are also given here. The first thing is I'm going to put 25 ml of the hydrochloric acid solution. This is a solution of unknown concentration. So I will put 25 ml of this solution in a conical flask, and I'm going to fill a burette with the standard sodium hydroxide solution, and the actual concentration of sodium hydroxide is given here. Okay. So just a reminder, you have seen these two pieces of equipment before. You've used it in the past. So the way that a titration works, this is the representative setup of a titration experiment. You have a conical flask. Now, ignore the color for now. We'll talk about the color change next week. But in the conical flask, as suggested by the question, I'm going to put HCl. So the hydrochloric acid is going to be in the conical flask, and the volume of HCl is 25 ml. So I will put 25 ml of hydrochloric acid in the conical flask. I'll talk about what equipment you use to put this 25 ml in next week. And then I'm going to fill the burette. Now, you all have seen the burette and you've done at least one experiment using the burette. Just remember that it's one of these tubes, and then you have like almost like a faucet here, so you can dispense the solution drop by drop, and then you can control exactly what volume of solution is being dispensed when you use a burette. So it's a very useful piece of equipment. So the burette in this case is filled with sodium hydroxide. So in the burette, I have sodium hydroxide. So whenever you have a titration experiment, you always have a burette and then a conical flask. One solution is going to be in the burette and the other solution is going to be in the conical flask. The concentration of this solution is 0.170 molar. Okay, let's keep reading. The sodium hydroxide is then, that should say then, gradually added to the conical flask. So you're going to turn on the burette and then add the sodium hydroxide to, add the sodium hydroxide to the conical flask gradually. And as you add the sodium hydroxide to the hydrochloric acid in the conical flask, what is going to happen here is that you're going to have a chemical reaction. So sodium hydroxide being added, it's going to react with the hydrochloric acid in the conical flask and neutralize it, and then you're going to get sodium chloride and water as the two products. So as you add the base to the acid, or as they say, drop the base into the acid, there will be a neutralization reaction occurring in the conical flask, and the solution will gradually become neutral. Now the key thing here is that you're going to stop adding the sodium hydroxide at the point when you achieve what is called a complete reaction. We'll talk about what a complete reaction is in a little bit more details next week, and we'll also talk about how do you know when to stop. So all of that technicality we'll talk about next week. So let's just assume that magically I know when I'm supposed to stop adding the sodium hydroxide. And you're supposed to stop when you have a complete reaction. In other words, when you're going to turn off the faucet and stop adding the sodium hydroxide when you have just enough sodium hydroxide to react with all of the hydrochloric acid. So you have just enough NaOH to react with all the HCl. And if you have just enough NaOH to react with all of the HCl, this is another way of saying that none of the substance is in excess. You have a complete reaction. The sodium hydroxide is not in excess. You have just the right amount. Everything reacts completely. So at the end of the experiment, you don't have any excess sodium hydroxide or any excess hydrochloric acid. So no excess. I mean, it wouldn't really make sense to say that both reactants are limiting, but I guess you can think of it that way. So both of the reactants are used completely. Okay. Oh, the last thing that is given here is that an average titer of 16.5 mil is required. So when you use a burette, if you record the initial reading and then the final reading, let's say that's 16.5, then you can tell how much sodium hydroxide has been added into the conical flask. So the volume of sodium hydroxide required is 16.5 mil, and the volume of the solution in the burette that you need for a complete reaction, that volume is called a titer. Titer? I've been saying titer, so I'm going to stick with titer. So the titer, this is the titer, which is the volume of the solution in the burette that you need for complete titration. Okay, I'm going to continue. Let's just revise what we just talked about. So you have a titration experiment. In the conical flask, I have hydrochloric acid, and the volume of hydrochloric acid that is used is 25 ml. In the burette, I have a solution of sodium hydroxide. The concentration of sodium hydroxide was 0.17 molar, and the volume of sodium hydroxide that I need for a complete reaction, meaning there's no excess, is 16.5 ml, and this is also the titer. So the volume that comes out, the volume of the solution that comes out of the burette is called the titer. Now, I also give you the equation here, so it's a 1-to-1 reaction mole ratio, so it's nothing too exciting. And ultimately what you need to do is you need to determine the concentration of HCl. So concentration is the unknown. Okay. So this is actually probably as simple as it gets when it comes to a titration experiment. You given the concentration and volume of sodium hydroxide, you know that a complete reaction has occurred between sodium hydroxide and hydrochloric acid, and you need to determine the concentration of the hydrochloric acid. So step one is going to be finding the number of mole of sodium hydroxide that has reacted. Because you have a complete reaction, you don't need to worry about limiting excess in this case. So I'm just going to find N of NaOH, which is concentration times volume. You need to convert the volume to liter, so you're going to have 0.17 times 0.0165. Okay, I'm just using a calculator here. 0.17 times 0.0165. So the number of moles of sodium hydroxide is 0.002805 mole. All right, so basically around this many moles of sodium hydroxide was used to react with all of the hydrochloric acid in the conical flask. So once you've determined the number of moles of sodium hydroxide that you used, you can then use mole ratio to determine the number of mole of hydrochloric acid that must have been present in the conical flask, because you have a complete reaction between the two substances. So I'm going to use mole ratio here because I have the equation. I mean, you don't have to use mole ratio, it's 1:1, but let's just, for the sake of consistency, I'm going to write unknown, so I need to find the number of mole of hydrochloric acid, and I have the number of mole of sodium hydroxide, and it's a 1:1 ratio according to the equation. So the number of mole of hydrochloric acid must be the same as the number of mole of sodium hydroxide, so it's just 0.002805 mole. So basically you need to make a jump from what happened in the burette to the conical flask, so going from the burette, because the number of mole of sodium hydroxide is the burette, and we're going from burette to conical flask here. And in order to make that connection between the burette and the conical flask, you need to rely on mole ratio. Once you've found the number of mole of hydrochloric acid that must have been present in the conical flask, you can find its concentration. Now, the question didn't specify which unit of concentration is required, so any unit of concentration is acceptable, except as long as you actually write the unit down. Normally, we'll go with molar concentration because we already have the number of mole. But if you really like to do percentage mass per volume, don't let me stop you. Just make sure you do the calculation properly. But then why would anyone want to do extra steps? So I'm just going to convert the volume to liter as well. So I have 0.1122. I'm gonna go with 3 sig fig this time because the minimum number of significant figures in the question is 3. So this is the concentration of hydrochloric acid. Remember that the purpose of a titration experiment is to determine the concentration of a solution. So at the end of the calculation, you should end up with a concentration of something. All right, let's do another example. The way that a titration experiment is normally described is they would just tell you what all the steps that happens. Okay, that's supposed to be a full stop. So one thing that I normally recommend students to do when they read these questions is to draw some sort of a diagram or flowchart, and that can help you follow the steps and not miss anything. The better you are at drawing these steps, the faster you'll be able to tackle the questions. When you get very, very good, you don't have to draw anything at all, but especially when you start out and you have a very long question with many steps, I do recommend drawing each step. So I guess I'm going to draw this one twice. All right. To determine the concentration of ethanoic acid in vinegar. Oh no, that was supposed to be a comma. That's not supposed to be a capital. All right. So the first piece of information, I know that I need to find concentration of ethanoic acid. Another way to sort of cut out on time and be more efficient is to summarize as you read. So instead of reading the whole thing and then do the summary, what I tend to do is I will translate and extract information as I read. So I only have to read the question once to get all the information. So the first part, and this is not to, you cannot skip any part, all right? So read every word, but just summarize you go. To determine concentration of ethanoic acid. So The first part tells you the purpose of the experiment, which is to determine the concentration of ethanoic acid. A 25 ml sample of the acid. So the first thing that happened here is ethanoic acid. You have ethanoic acid, and the first thing is I take a 25 ml sample. So whenever you determine the concentration of something, obviously you need to take a sample of that substance. Say, for example, if I have a bottle of vinegar in the kitchen and I say, well, I want to work out the concentration of this vinegar, you're not going to use all of the vinegar. You take a little bit of that vinegar and then you use that in the experiment. So you always take a sample of what is it that you're trying to find the concentration of. So we have a 25 ml sample of ethanoic acid, and you dilute it to 100. So the 25 has now becomes 100 ml. Just to make this very clear, to know what this step is, this is dilution. I'm going to call the original solution 1 and the diluted one 2. And I'm going to remind myself of the dilution formula, C1V1 equal to C2V2. So I'm just going to write all of that here, and hopefully that will help me later in doing the question. All right, what happens next? A 20 ml sample of this diluted solution. So this diluted solution refers to the 100 ml. So once you've diluted, you take a 20 ml sample. So there is a process of sampling here. And you have another volume is 20 ml. If you want, you can call this solution 3 just to distinguish between this one and the other two solutions. You can also remind yourself of the connection between a solution and the sample. So the concentration of the two solutions will be the same. C2 would equal to C3, for this being solution 2 and this being solution 3. All right, what happened? A 20 ml sample of this diluted solution is then taken and titrated with 0.114 molar sodium hydroxide. Okay, so the solution that you already know the volume of is going to be the one that ends up in the conical flask. Whenever you see the word titrated, it means that a titration has taken place. So the 20 ml will be in the conical flask, which means that the sodium hydroxide must be in the burette. And I can't draw, so my burette looks like a pencil, but we'll just get used to it. All right, so this is a burette, and in the burette you have sodium hydroxide, NaOH. The concentration of sodium hydroxide is given in the question is 0.114 molar. And last sentence, the titer required. Now the titer refers to the solution that comes out of the burette. So the titer must be the volume of sodium hydroxide here. So the titer is 15.45 ml. Okay. And then, oh, I need to fix the equation. All right, this is supposed to be NaOH. I think I fixed it in the worksheet, but I forgot to fix it here. This question is actually the next question. Just ignore what I just said. Okay. And then you need to determine, once again, determine the concentration of acid in the original concentration of acid in the vinegar. So the original concentration refers to solution 1. So ultimately, what I need to find is C1. Okay. So I'm going to draw this again on a new page so I can actually do the calculations. Obviously, if you print the worksheet out, then you should have the whole thing, and you can make it go down if you want. So we have CH3COH. Just to recap, you start with a volume of 20 ml. So you take a 20 ml sample and then you dilute it to 100 ml. So you create another solution of ethanoic acid. Let's call it solution 2 with a volume of 100 ml. Just to remind myself, C1V1 would equals to C2V2 because this is dilution. You then take a 20 ml sample of this diluted solution and then put it in a conical flask. So the diluted ethanoic solution is now in the conical flask. Let's call this solution V3, which is also 20 ml. And just to remind yourself, this is still ethanoic acid. Now, when you take a sample from an original solution, my conical flask is terrible. Let's draw it again. You don't have to draw it again. Oh God. This is the thing I waste my life doing. redrawing conical flasks. All right, that's not any better, but we're going to leave with that. What was I saying? Yes, when you take a sample, the original and the sample will have the same concentration, which means that C2 would equal to C3. Now, this sample of diluted ethanoic acid is titrated against a solution of, I can't draw a straight line, a solution of sodium hydroxide, and the sodium hydroxide is in the burette. Seriously, it just keep getting worse. You know what? This is about the time when probably should just draw a pencil and be done with it. Okay, so you have NaOH in here. The concentration of NaOH is 0.114, and in order to achieve a complete reaction, so nothing is in excess, so all of the ethanoic acid is reacted with sodium hydroxide, the volume of sodium hydroxide that I needed to use was 15.45 ml. 0.45 ml. And ultimately, what I need to find is the concentration of the original solution. So let's put that in a box so we know that we ultimately has the end here at this point. Oh, and obviously you also have the equation, which I'll rewrite underneath maybe up here, CH3COOH plus NaOH. I'm only after the mole ratio here, so I'm not doing the states, which I'm sure is fine because this is not a question that you need to do anyway. Okay, so always start with the part that you have the most information, which in this case is going to be the standard solution of sodium hydroxide. The first thing I'm going to do is I'm going to find the number of mole of sodium hydroxide by concentration times volume. Make sure you convert the volume to liter. Alright, so the number of mole of sodium hydroxide is 0.00176 mole. Okay. So this many mole of sodium hydroxide is used in the reaction, and the reaction is between sodium hydroxide and ethanoic acid. So the sodium hydroxide actually goes down to here. So from sodium hydroxide, we now need to make the jump going from the burette to the conical flask. And so that's going to be step 2. And in order to connect what happens in the burette, or what is in the burette, to what is in the conical flask, I'm going to need to use the mole ratio between the two substances in the equation. So I'm going to use mole ratio, which so far has been a 1-to-1 mole ratio. The mole ratio between ethanoic acid and sodium hydroxide is 1-to-1. Therefore, the number of mole of ethanoic acid is going to be the same as the number of mole of sodium hydroxide. So it's 0.00176 mole. And this is the number of mole of ethanoic acid in the conical flask. Okay, so let's call this N3. It is N3 of the third solution of ethanoic acid here. All right, so let's recap what we've done so far. We have worked out the number of mole of sodium hydroxide, and from this step, we basically have N3, which is the number of mole in this original solution. I need to go back to C1 because there are actually 3 solutions of ethanoic acid being involved in this equation. So in order to go from the solution in the conical flask back to this 100 ml diluted solution, so let's say this is 1. This is actually, I'm not going to do that. What I'm going to need to do is I need to take advantage of the fact that between an original solution and the sample, the concentration doesn't change. So once I've found the number of mole of the solution in the conical flask, the next thing that I'm going to do is I'm going to find the concentration of ethanoic acid in the conical flask. So C3 is going to be N3, which you just found, over V3. Now, once again, please convert the volume to liter. So the concentration of ethanoic acid in the conical flask is 0.088 molar. All right, so beside V3, by calculation, we have found N3, which is 0.00176 mole. And then from here, from step 3, we have found C3, which is the concentration of this solution, which is 0.088 mole per liter. Now, because this is a sample of the second solution, I can also write here that C2 must equal to 0.088 molar as well, because the sample and the original should have the same concentration, because C2 equals to C3. Now, once I have C2 and V2 and V1, I can now work backwards to work out the concentration of ethanoic acid in the original solution. So I can just go C1 equal to C2V2 over V1. So you have 0.088 times 0.1 over 0.02. So final answer is 0. All right, we're gonna go with 3 sig fig, 0.440 mole per liter. So this is the original vinegar, ethanoic acid concentration in the vinegar. So if you can draw out a proper flowchart, you can do all of your working out on that flowchart, and you start at the end and then you work backwards. Okay, so this is, if you want, this is step 4 is to find C2, and then step 5 is to find the original concentration. So get into the habit and really practice summarizing the question as you read it. It will save you a lot of time and also make it a lot clearer in terms of what you need to do. If you just skim the question, you're probably going to skip and miss some of the dilution and sampling steps. Okay, so I leave question 3 for you so you can do yourself. I do think that the question is actually different. Okay. I think I'm gonna do this one. So I'm gonna do this one. Maybe I won't do this one. I will, however, summarize the question for you and then see whether you can do the question from my summary. The only extra thing with this question is you have to write the equation out yourself. Okay, a 0.1 molar magnesium hydroxide. So you have a solution of magnesium hydroxide. Maybe I should do this question actually. The concentration is 0.1 molar. I don't know where to go from here yet. A 0.1 molar magnesium hydroxide solution is used to find the concentration of a solution of nitric acid. So the end game here is we want to find concentration of nitric acid. So let's just write that somewhere just to remind ourselves that this is the ultimate purpose of this experiment. An aliquot, okay. I'm not going to tell you what an aliquot is just yet, so let's just say a sample, and then I'll talk about aliquot next lesson. A sample of 25 ml of magnesium hydroxide is added to a, let's say, conical flask, just to be clearer. So this one is a little bit interesting because it actually puts the standard solution in the conical flask. So this solution goes into the conical flask. If you remember the previous example, the standard solution was in the burette, and then the unknown solution was in the conical flask. But in reality, there is no rule that you have to have which solution in which piece of equipment. You just need one solution in the conical flask. So in this case, the magnesium hydroxide is in the conical flask, and the volume of magnesium hydroxide used is 25 ml. So I'm going to rewrite here, MgNOH is in the conical flask with a volume of 25 and the concentration of 0.1. All right, which means that the nitric acid is going to be in the burette. You know, it doesn't actually say that this is a titration experiment, so I may have to fix that. I just write the word titration at the start. Okay, so the volume of nitric acid required to neutralize it, so HNO3, is in the burette, and the volume of nitric acid required was 13.5 ml. And then they tell you again, calculate the concentration of nitric acid. So you need to find the concentration of nitric acid in the burette. Okay, this is actually not too bad. There is no dilution and sampling. So once again, I'm going to start at the point where I have the most information. And in this case, always is going to be the standard solution. But the standard solution is just in the conical flask here. But the steps will not change. So first thing I'm going to do is to find the number of mole of magnesium hydroxide, which is concentration times volume. So please remember to convert the volume to liter. I feel I should be able to do that calculation by hand, but okay. So the number of mole of magnesium hydroxide that was used is 0.0025 mole. So in this particular question, you're going to have to go up, if you will. So you start with the conical flask, and now you have to make the connection between the solution in the conical flask and the solution in the nitric acid. And once again, in order to make that connection, you need to use mole ratio. Now, one extra thing about this question is that the equation is not given, so you need to write it out yourself. So the reaction that happens when you mix nitric acid and magnesium hydroxide together is, all right, I probably need more space than that. Let's just write it here. So MgOH 2 plus HNO3 going to Mg, oh geez, okay, and then water. So you're going to need to double the number of acid because you have two hydroxide groups here. When you get very good, you don't even need to write the equation now. You should be able to work out the ratio between the acid and the base just by looking at the formulas. But that's probably for next year. So once you have the equation, you can find the number of mole of nitric acid using mole ratio. So MgOH2, this is a 2-to-1 mole ratio, which means that the number of mole of HNO3, it's going to be double the number of mole of magnesium hydroxide. So 0.0025 times 2, which is 0.0050 mole. So this is how many mole of nitric acid you actually have in the 13.5 ml titer. So once you've worked out the number of mole of the acid, the last thing to do is to find the concentration, which is going to be number of mole divided by volume. Another reason why I think it's a good idea to draw this out is because there are two different volumes given in this question, and students always get mixed up which volume is for the acid and which volume is for the base. So it's important to summarize the question as you go so you don't get confused with these things. All right, so I have 0.37, I'm going with 2 civic this time because that's 2 civic. So the final answer, 0.37 mole per liter is the concentration of nitric acid in this solution. All right, so you can do 5 yourself. I think actually I'm going to summarize question 6 for you because there's just way too many things going on in question 6. So I'll do the summary and then you see whether you can do the question yourself. So let's just start with the summary. Let's hope I can squeeze the whole summary in here, but you should draw it out with more space so you can just fill in the answer. To determine the concentration of hydrochloric acid, so I want to know concentration of HCl in brick cleaner. A student first diluted a 20 ml sample. So you start with HCl, you have a 20 ml sample. So V1, you're going to dilute, so you're going to have more than one solution of HCl. V1 is 20 ml. You dilute it to 250 ml. In a volumetric flask, I don't know whether anyone remember the volumetric flask is the one with like a really long neck, and then anyway, you know, there's the 3 sizes that I show you. I was going to draw it, but I can't draw the volumetric flask properly. I'll show you a picture next time. Where was I? Yes, V1 is 20 ml. We're going to dilute it to 250 in a volumetric flask, okay? Dilution formula C1V1 equals to C2V2. When you have something like brick cleaner, it's common practice to actually dilute it before you conduct the experiment because it's so concentrated that you would need a lot of sodium hydroxide for a complete reaction. So in order to save resources, it's better to dilute it. It's also safer when you dilute it because it's highly concentrated. All right, the student then added this diluted solution to the burette. So the diluted solution, oh, this question's good, okay, goes into the burette. All right, they prepared a standard solution of sodium carbonate. So there is sodium carbonate here. And the sodium carbonate, you start with mass. So the mass of sodium carbonate, maybe I should do this question. You don't, okay. I always draw a scale. I don't know why. You don't actually need to, so I'll stop drawing the scale so it doesn't waste your time. But yeah, every time I say mass, I do like a full-on scale and then just put 1.34. And then I was looking at some of the work of the year 12 students this year, and I said everyone's drawing the scale, and I feel like that was the one thing that I imparted on them. What was I doing? Yes, so you add 1.34 grams of sodium carbonate and filling up to 250 ml with water. So you basically dissolve all of these 1.34 grams into a solution of 250 ml. Okay. And then what do you do next? You took a 20 ml sample of this solution. So there is a sampling here. And you're going to put it to a conical flask. What is that? All right. I have way too many solutions. I don't know whether I'm going to call this solution 2, 3, 4. So I'm just going to say same C here instead of say C2 equal to C3 because I don't know which number I'm going to go with this solution. And the volume of this solution is 20 ml. Okay, move up to here. So the sodium carbonate is in the conical flask and the acid is in the burette. A titration was conducted and the average titer obtained was 12.86 ml. Now, this is not very explicit in the question, but when you put the solution of HCl in the burette, you don't actually use all of it. So you only use 12.86 ml of the 250 ml solution. So you have 250 ml solution, you put it in the burette, but you only dispense 12.86 ml. So really what happens here is you have a sampling. You can think of the amount of hydrochloric acid that you have used as being a sample of the 250 ml solution. So this is a sample. The 12.86 ml is a sample of the original solution, and you should treat the relationship between those two solutions as such. As you put some in the burette, and then you only take out 12.86 ml to add to the conical flask. Determine the original concentration of acid in the brick cleaner. So I need C1 here. All right, this question is good because you probably want to start here, just a hint. So once again, if you take a sample, then these two solutions have the same concentration. Okay. Anyway, I may not spoil it actually, so you should try this yourself and I can help you if you need to, but you can use this summary as a guide in terms of what to do. And then lastly, try question 7, question 8, question 9, and question 10 yourself. For question 10, you actually have to calculate the average titer because the results of 3 different trials are given. All right, and that is that. Thank you.